Hi everyone, I am here to discuss about the basic concept of a PN junction. First of all, let's go through the topics we are covering. What is a PN junction? Basic structure, biasing of PN junction, VI characteristics and its applications. First we are going through what is a PN junction. Basically, a PN junction is simplest semiconductor device. It is a boundary in between a p-type and n-type material in a single crystal of semiconductor. Diode is the term to refer a PN junction. Now let's see the structure of a PN junction. In the basic structure, on the n side, the electrons are the majority carriers. Some holes are the minority carriers. On the p side, holes are the majority carriers and few electrons are the minority carriers. The red colored dots represent the electrons and the white dots represent the holes. Also we can see the basic circuit representation of the PN junction, with the P side act as an anode and the N side act as a cathode. Next we are discussing about biasing of a PN junction. Biasing is a process of controlling the operation of PN junction by applying some external potential. The type of biasing is based on the external potential applied across a PN junction. Before that, we are discussing about the equilibrium condition of PN junction. So, let's see the equilibrium condition. In equilibrium condition, there is no external potential is applied across the P and N terminals. The figure shows the initial stage of PN junction formation. In this condition, the P and N sides contains a sharp majority carrier concentration. Now, this is the carrier concentration gradient in P and N sides of a PN junction under equilibrium. The red curve shows the carrier concentration of electrons. It is higher in N side and decreases from N side to P side. Since the carrier flows from higher concentration to lower concentration, electrons flows from N side to P side. Similarly, the black curve shows the hole concentration. It is also higher in P side and decreases from P side to N side. Thus, the holes moves from P side to N side. This carrier concentration make a current flows across the junction. This current is known as the diffusion current. Both the carrier flow of electrons and holes make the diffusion current. The red arrow shows the electron diffusion from N side to P side and green arrow shows the hole diffusion from P side to N side. The electrons diffused from N side will recombine with the holes in the P side. As a result, some negatively charged acceptor ion left in the P side and a positively charged donor ions are left in the N side. These are the immobile ions. The deposition of these immobile ions on either side of the junction create a region is called depletion region or space-charge region. The depletion region is depleted of mobile charges. So, it contains only immobile charges. Here the figure shows the recombination process and formation of immobile charges. This gives the number of electron-hole pair recombines is equal to the number of positive and negative immobile ions formed. Due to the opposite immobile charges, there is a dipole effect in the depletion layer. So, there is a potential difference exists in the depletion layer. Hence, an electric field emerges in the depletion region, which is directed from N side to P side. In this figure, E represents the electric field and the arrow shows its direction. Now let's see some important properties of depletion layer and then we can move to the diffusion process. In depletion layer, the number of positive ions in N side is equal to the number of negative ions on the P side. The width of the depletion layer decreases with increase in doping. That means a highly doped semiconductor has a narrow depletion region and a lightly doped semiconductor has a wide depletion region. If the doping concentration of P side and N side are equal, then the width of the depletion layer also will be the same on the both sides. Since the depletion layer contains charges, it has higher resistance compared with the other regions of semiconductor. Now, let's continue with the diffusion process. As the diffusion process continues, the width of the depletion layer increases and the electric field gets more strength. As a result, the depletion layer acts as a barrier for the majority carriers to move across the junction. Thus, diffusion current decreases and ends gradually. At the same time, there is an opposite current which arises is called drift current. The drift current is due to the thermally generated minority carriers on both P and N sides. And these minority carriers will drift across the junction with the help of the electric field. We can see the formation of both diffusion and drift current here. In figure 8, the diffusion current is due to the majority carriers that hole diffused from P side to N side and electron diffused from N side to P side. Also, in figure 9, we can see that the drift current is due to the minority carriers. So, in equilibrium condition, the drift current and diffusion current are equal and opposite. Thus, the net current is 0. So, there is no current flow in the PN junction under equilibrium. So, we are reaching in some conclusions as diffusion current decreases, drift current increases. In thermal equilibrium, the net current is 0. The potential difference exists in the depletion layer at equilibrium is called built-in potential or contact potential. This potential difference makes an energy difference. It is denoted as delta E, which is equal to Q into V0, where Q is the charge of an electron and V0 is the built-in potential. Now let's see the PN junction under forward bias. Applying a positive potential to P side with respect to the N side is called forward biasing a PN junction. The applied bias voltage creates a field from the P side to N side, which is opposite to the built-in field. Thus, the resultant electric field across the junction under forward bias will reduces as compared to the built-in field. Hence, the potential barrier at the junction also reduces to V0 minus Vf, where V0 is a built-in potential under equilibrium and Vf is the forward bias voltage. As the bias voltage weakening the field, the energy barrier reduces so that the resistance of the depletion layer is also decreases. So, more electrons diffuse over the barrier from N side to P side and more hole diffuses from P side to N side. This results the increase in electron and hole diffusion current. And there are some minority carriers. The holes in N side is attracted to the negative terminal of the applied voltage and electrons in the P side is attracted to the positive terminal of the applied voltage. So, the drift current is very negligible and thus the major current is flows due to the diffusion from P side to N side. Next we can see the reverse biasing of a PN junction. In PN junction under reverse biasing, applying a negative potential to the P side with respect to the N side is called reverse biasing. The reverse bias voltage is enhances the built-in field. It's resulting a higher electric field. But a higher electric field can sustain only if a large amount of positive and negative immobile charges present in the depletion layer, so that more deposition of these immobile charges will result a wide depletion layer. So, the potential barrier at the junction is increases than in equilibrium. That is V0 plus VR, where VR is the reverse bias voltage. As the width of the depletion layer increases, the resistance is also increases. Thereby, diffusion currents are negligible. Therefore, the net current is relatively small drift current from N side to P side. This current is due to the drift of thermally generated minority carriers. This current is also called reverse saturation current or leakage current. Next we can see the IV characteristics of PN junction. The figure shows the IV characteristics of PN junction under both forward bias and reverse biased conditions. In forward bias, the current is increases exponentially with increase in forward bias voltage. The change in forward current is large for a small change in forward voltage. Therefore, the resistance of diode under forward bias is very small. In reverse bias, the current is due to the minority carriers remains constant. It can see in the figure and the current is almost independent of voltage. So, the reverse saturation current is very small and which is in the order of microampere in germanium and nanoampere in silicon semiconductors. Finally, let's discuss about the applications of PN junction diodes. This device has many applications in electronics. The diodes are used in adapters which are used to charging the batteries of cell phones. Also, it is used in many circuits like rectifiers. Rectification is a process of converting AC voltage to DC voltage. Next, the voltage regulators. Voltage regulators are used to maintain a constant voltage at the output with the help of a feedback system. Mainly, the Zener diodes are used as voltage regulators in electronic circuits. The Zener diodes are works under both forward bias and reverse bias conditions. But the reverse bias condition of the Zener diodes is mostly used. The PN junction diode in reverse bias is very sensitive to the visible light, which is used as photodiodes. The photodiodes are absorb the light and convert it to the electric current. So these are used as solar cells. LED is the most important application of diodes. The PN junction under forward bias is used in all lighting applications. LED is a semiconductor light source that is emit light when current flows through it. So we can see the LED with different colors corresponds to the energy of photons. So we have studied about the PN junction basics, biasing and some of its applications.